Hello friends, today we will study LZB system, which stands for Linienzugbeeinflussung. German word, simply train control system. LZB is a continuous train control and signaling system developed in Germany and widely used in German high-speed and main lines. In Spain, this was installed on Madrid Seville High-Speed line, the country's first AV line. Unlike point-based systems such as ASFA, LZB provides continuous communication and supervision, making it suitable for high-speed operations. LZB is a continuous signaling and train protection system. It uses inductive loops installed in the track to transmit information continuously to the train. This continuous communication allows permanent supervision of train speed, calculation of braking curves, transmission of target speed and distance to the train. Because of these features, LZB marked a major technological step beyond punctual supervision systems. Why LZB in Spain? When Spain inaugurated its first high-speed lines in 1992, a system capable of handling very high speeds safely was required. LZB was chosen because it provides continuous supervision, not just spot checks. It introduced the concept of target-based driving, where the driver follows speed and distance objectives. It forms the technological basis of what we now call automatic control block, BCA. At that time, LZB was one of the most mature and proven continuous ATP systems in the world. System architecture. Like most signaling systems, LZB consists of two main parts: trackside equipment and on-board train equipment. The key difference compared to ASFA is that in LZB, communication is continuous. Communication is bidirectional, and the train is permanently connected to a central control post. This architecture enables dynamic supervision of train movement. Trackside equipment. The trackside equipment of LZB mainly consists of an inductive loop laid between the rails. Important characteristics: operating frequency 56 kHz, data transmission speed 1200 band. One loop can theoretically cover up to 48 km, but for safety and reliability, this is limited to 12.6 km. Additionally, every 100 meters, the loop crosses itself. These crossings serve as a reference points for train odometry, allowing precise position determination. On-board equipment. The on-board equipment of the LZB consists of an antenna, a connection to the emergency brake, a central processing unit, and a driver-machine interface. All safety supervision, braking calculations, and driver information are handled by this onboard equipment in real time. The antenna has two main functions: to send and receive information through the inductive loop, and to assist in synchronizing the train's odometry system. The processing unit is microprocessor based and performs critical tasks such as calculating braking curves, determining permitted speed, and computing target speed and target distance. This makes LZB a fully dynamic control system. Driver Machine Interface (DMI). The LZB Driver Machine Interface provides the driver with three essential indications: limit speed, the maximum speed allowed at that moment; target distance, the distance to a point where speed must change or becomes zero; target speed, the speed the train must have at that target point. At the bottom, there is a light panel and three push buttons. These act as the signaling interface, requiring driver acknowledgement and ensuring interaction with the system. System operation. The operation of LZB is fundamentally different from ASFA. In ASFA, the train acts largely as an isolated unit, receiving punctual information. In LZB, communication is continuous. Communication is two-way, and a central control post is mandatory. The train continuously sends its position data, and the control post continuously sends moment authority and speed data. Central control post. The central control post stores all fixed geographical data of the control area, including entry and exit points, track circuits, switch positions, gradients, and maximum permissible speeds. The train reports its exact position, and the control post responds with updated moment parameters to ensure safe operation. Braking curves and supervision. Using the received data, the onboard system dynamically calculates permitted speed, braking curves, and target points. If the train exceeds the allowed speed or fails to follow the braking curve, the system will automatically apply the emergency brake. This ensures safe stopping before signals, speed restrictions, or the end of movement authority. To conclude, LZB is a highly advanced continuous ATP system. It enabled safe operation of early high-speed railways. It introduced target-based driving and continuous supervision. It laid the foundation for modern systems like ERTMS or ETCS. Although newer systems are now being adopted, LZB remains a landmark technology in the evolution of railway signaling. Okay, thank you.